So we prove this theorem. This is an important theorem. We take a rectangle. Because the integral of f over a subset D is defined using integral of rectangle. So to deal with the integral over general subset, we always take a rectangle containing D. Okay. Take a rectangle I containing D. Then D has Jordan content 0 for any epsilon daily positive. There are rectangle I that is I1 IN such that D is contained in the union of the interior of II, and the total volume of the rectangle is less than epsilon. Okay. Now we process as in the proof of the important theorem that if the discontinuous point forms a Jordan content 0 set, then f is integral. Similar to that, to the proof of that theorem, let AI 接 BI 接 B the GS edge of II. And construct PJ. PJ is the union of all these endpoints, that is AIJ, BIJ, and intersecting the IJ. The notation here, IJ is the GS edge of our rectangle I. Okay. Then this PJ is the maybe this is not very accuracy. So anyway, we added the endpoints of the GS edge of II into the GS edge of I. So obtained a partition of the GS edge of I, denoted by PJ. Then the P1 close Pn is a rectangle. It's a partition of our I. Okay. In picture we write. So this is the rectangle I, and so as before, this is our D, and maybe similar to the proof of the previous theorem, and this is I1, I2. So consider the first edge of I. The first edge of I has endpoint here. This endpoint and this endpoints. Now we take the endpoints of each I1 in this picture, I1 and I2. The first edge of this I1 and I2 are those points here. Okay, so we have this point. We add the red point into the edge of I, and also in the other direction we also do the same thing. So we have this point, this point, this point, and this point. Of course, this point. So this point determines a partition of our rectangle. I. Okay. So as before, the rectangle in this for this partition contains two classes. One class is those containing in the union of II. That is corresponding to the yellow one. That is this rectangle. The other rectangle is those not containing in the union of II. For example, this rectangle. Okay, the red and the blue rectangle are two classes. So all the rectangle of this all the sub rectangle of this partition can be categorized into two classes. For the first class, that is the red one, P1. P1 is J contained in the union of I. And the P2, for P2, is J not contained in the union. Okay, we have only these two classes of rectangle. Now, if J belonging to the first class, I should write this in another way. Okay, so if J belonging to the first class, then maybe we consider we consider P2 first. J belonging to the second class, then the intersection of J and D is 0. It's empty set. Therefore, FD is empty when such J. So, for example, in this rectangle, because FD is this blue curve is D. The blue curve is D. So FD is the 0 extension of F with respect to D. Therefore, outside D, FD is 0. So for such a rectangle of the second class, the FD is 0 on that rectangle. Okay. And if J is from the first class, then FD might not be 0, but the supplement of FD over such rectangle is not 0, but this will not greater than the upper bound of our function f. Because over the whole rectangle I, f is not greater than b. Therefore, for every subrectangle, the supplement of f over that subrectangle could also not possible to be greater than b. So we have this inequality. Okay. Now we consider the upper sum of our function f over this with respect to this partition fd. Our function fd, the 0 extension of f outside D, with respect to D, with respect to this partition P. This is the sum of all rectangle NJFD with G. So the rectangle, we have two classes of rectangle, the first class and the second class. For the second class, fd is 0. For the second class, fd is 0. Therefore, mjf is 0. So this sum only remains we only have the j from the first rectangle. But for such a rectangle, all the mj will not greater than b. So this will not greater than b. But the sum of all the first class rectangle is precisely the total volume of I1 and I2. Okay, so this is precisely b I from 1 to m. So this is not greater than epsilon. Okay. So this means that for any epsilon positive, we can find a partition of P. We can find a partition P of the rectangle I such that the upper sum of FD over that partition, with respect to that partition, is not greater than B epsilon. So the upper integral of FD over the rectangle will not greater than, in fact, is strictly less than B epsilon. And similarly, you can prove that using lower sum, you can prove that the lower integral of FD over the rectangle I is greater than minus B epsilon. Now, since epsilon is arbitrary, we see that the upper integral equal the lower integral. They must be 0. So this means that the function is integrable and the integral is 0, proving the first part of this theorem. Okay, the first part of this theorem. Now let's go to the second part. To prove the second part, we take a rectangle I containing D, and we consider a function phi defined, bounded function defined over the rectangle I. So we can consider such a bounded function as a map from I to interval. So if P is a partition of our rectangle I, what will happen? We know that absolute value of phi x minus absolute value of phi y, then absolute value will not greater than the absolute value of phi x minus phi y. This is a triangle inequality. So from this triangle inequality, we see that for the absolute value function, this will not greater than the original function. And so the difference between the upper and the lower sum for the absolute value function will not greater than that of the original function with respect to the same partition. So this inequality tells us that if phi is integrable, then the absolute value is also integrable. So if phi is integrable over the rectangle I, then the absolute value function also integrable over the rectangle. Furthermore, the function defined in this way, phi absolute value plus phi or minus phi, then divided by 2. This is also integrable over the rectangle I. In another way to define the phi plus is maximum, phi and 0, and the phi minus is the minimum. Phi minus is the maximum of minus phi 0. Okay, but the maximum and the minimum is difficult to study, but you can use the alternative definition. That is, the phi plus and the phi minus is linear combination of the absolute value function and the original function. So we have known that for function over rectangle, the linear combinations are also integrable. Okay, therefore phi plus and phi minus are all integrable. Now, if we have another function, psi is another integrable function over the rectangle, then the minimum function of phi and psi, both phi and psi are integrable. Now their minimum is a new function generated from these two functions. The minimum can be expressed, as you can check, by psi minus the minor part of phi minus psi. Maybe, okay? You can prove this equality very easily.